Hello, everyone. How are we doing today? For those of you out there on the internet, please let me know if microphone is oriented correctly so you can hear me clearly. I've been using a easier to keep set up mic for about a week, so I'm out of practice with this little Bluetooth thing that I use when I'm in the classroom. But I am back in the classroom today. And then for those that were asking, I feel better. The Thursday, I think, is kind of when I started to turn the corner as far as not actually feeling ill, but I have a little bit of congestion I'm still dealing with. It's been very slowly diminishing over the past few days, so if I have a cough or sound a little bit off, that's what's going on there, but uh, not to the point to where I feel bad. It's just I can't promise that talking through an entire lecture I won't get caught a little bit and need to clear my throat. Okay, that's where we are on that. And where we are in the course is ready to start chapter 6. Okay. Now, for chapter 6, we are going to be moving in a different direction than what we've been talking about the past few days. And I just realized that needs to be added to this. Sorry, I'm setting up stuff in the background to show off later. Our website structure change, and there's something that it occurs to me. May not be available. We'll see. All right. Okay. All right. Sorry about the disruption there. I was correct in that link being broken, but I found a workaround that we'll be able to use in the short term and have to make an update to some other stuff. Okay. All right. So for chapter 6, the main idea that we're going to be working with is, of course, whatever these things called Laplace transforms are. All right. And what ultimately we want to do in chapter 6 overall is to convert a calculus problem to an algebra problem. Okay, this is our overall goal. We can, under certain circumstances, replace a complicated differential equation with a different expression and manipulate that expression algebraically. And then once we have manipulated it into the appropriate form, transform back to our original language and have that serve as the answer to our question. Okay? In order to do that, we have a little bit of setup work to do because we need to understand exactly how these kinds of transformations are going to be set up. Okay? So what we're going to be using, and the main tool here, is an example of an integral transform. The integral transform of note for these problems is a Laplace transform, but that is not the only type of integral transform out there. Okay, Laplace transforms are going to be the one that we're interacting with in this class, but another one that you may have heard of is known as a Fourier transform. Okay, so these are very common for ODE. And are also quite popular when it comes to doing electrical engineering problems, because they are quite good at dealing with the circuits examples that we talked about back in chapter 3. Okay. Fourier transforms are concerned with waves. All right. And there is a very important algorithm that you may interact with at some point in your careers that is referred to as a fast Fourier transform. Okay. And the fast Fourier transforms are popular because we use them for audio encoding. The basic idea behind these things is that we use sines and cosines to construct a basis, like we would have a linear combination of functions like we use for our solutions in the last couple of chapters for problems, except we of course would want many of these, many different functions that are all comprising things, and then you use the coefficients of the linear combination of these sines and cosines. So you would have, say, alpha 1 cosine t plus beta 1 sine t plus alpha 2 cosine 2t plus beta 2 sine 2t up to some cutoff point, like so, right? And then what you would do is all you need to do is store these numbers in order to know what the wave looks like, right? Because the functions don't change. And so what you do is for every short period of time, delta t, okay, you store that list of numbers. The shorter this period of time is, the higher your sample rate would be, right? And the more of these coefficients you track, the more of the audio band that you cover. Okay, more information, higher quality recording. And so the different types of audio encoding that you end up with are based on how many of these coefficients do you keep, how many do you throw away, and how high is the sample rate. So if you're going up to like a FLAC recording or something like that, it would be very, very high in both of those metrics. Okay, where something like an MP3 is relatively low. But if you're just playing it over earbuds or something, maybe you don't need all that fidelity. About what was the nature of the argument?
We were discussing MP3 files, and the difference between 180 Kbps and 360 can. That's a pretty big difference.
Yeah, that's, I mean, yeah. I see. So for the benefit of the recording, one of the students here has mentioned that they've been in an argument with one of their previous instructors about how important sample rate is when it comes to audio encoding, and I am aware that some people are more sensitive to it than others. I do know that there are some folks who's just they're not trained, so the quality differences aren't as impactful for them. But the people who are picky about it are exceptionally picky about it, uh, and can be sold things like $1,000 headphones that you shouldn't ever spend that much money on, unless you're like a professional music person where it matters. Uh, I personally am moderately picky when it comes to the audio stuff. The weird thing about me, where I'm overly sensitive, is vision correction. Um, for those of you who remember what I look like, I wear glasses, and whenever I go to see my optometrist, they give me a hard time because the smallest adjustments that they can make to my prescription, I can tell the difference. So I always end up with some overtuned nonsense with my corrected vision, where like it's like 2010 or something. At least in my good eye, one of my eyes is more well behaved than the other one. Anyway, so for integral transforms, this is the idea. We want to change the form of the problem to something that's going to be for us more convenient. And the transformation that we're going to be using for integral transforms, or for the Laplace transform in particular, pardon me, is going to look like this. The L here is an operator. An operator in mathematics is a function that returns another function as its input, or as its output. So you take as an input a function and you return a function as the output. We will, as a matter of habit, think that there is a relationship between functions based on them being named with a lowercase letter and a capital letter, just so that there's a clear corollary between these two things. Okay, but you'll notice that as these are written, one of them is considered to be a function of t, and the other one is considered to be a function of s. Okay? The transformation between these two functions is given by the integral from 0 to infinity of e to the minus st f of t dt. Okay? And so the idea is that once we compute this integral, all of the t's are going to vanish. What we will have left is a function that depends only upon s. And so what happens is we start off with a function that is written in this language here. And this is sometimes referred to as being in the t domain. We apply the Laplace transform to it, and we end up with this, which is in the s domain. Okay, the domain references, of course, are having to do with what the independent variable is for the function. All right. And then, of course, we may return by taking, if it exists, the inverse transform. To return to the t domain. Okay. Now, I'm going to try to avoid using this language, but occasionally when we're talking about integral transforms, we may refer to one domain as the time domain and the other domain as the frequency domain. This is less common in the language of Laplace transforms than it is in the language of Fourier transforms. In Fourier transforms, it is definitely the case where after you perform the integral transform, you are in the frequency domain. Here, I'll just refer to them as the T and S domains so that we can be clear about which space it is we're talking about. Okay? Now, looking at this, we see that this is an improper integral. So we need to make sure that we compute these appropriately, and we'll need to use limits when necessary in order to make all this work the way that it's supposed to. Okay? All right. So as a reminder, if we have the integral from 0 to infinity, let's say, well, let's integrate the function 1 over t dt. Well, sorry, we'll do a to infinity because we can't have 0 in the denominator. That's bad. So a is greater than 0. All right, what we want to do is we want to compute this improper integral here. And for the computation of this improper integral, whenever we write an infinity as one of our limits of integration, this is really what we mean. Allow one of the limits, or we take the limit as a approaches infinity of this expression. This is an integral that we can evaluate. The integral of 1 over t dt is, of course, the natural log of the absolute value of t. We evaluate this at capital A and lowercase a. All right. And because we are assuming that both of these quantities are positive, I can drop the absolute values. I forgot to write the limit here. That's bad of me. Put this over here out of the way. Okay. In the limit, this is some fixed constant. This increases without bound. So we say that this improper integral is divergent, right? Because it fails to have a finite value. Okay? Now, when it comes to Laplace transforms, this is not acceptable, right? We can't do math with divergent functions. So we need to make sure that when we do our computations that we end up with something that is finite, fixed, has meaning. And so what we need to do is do the work necessary in order to determine what sorts of things have reasonable Fourier transform, or reasonable Laplace transforms. Okay, so let's suppose that we have S that is greater than 0. And what we want to do is find the integral from 0 to infinity of e to the minus st dt. Okay. Now, as we just reminded ourselves, since this is an improper integral, we must recast it in terms of a limit expression in order to make sure that we are computing things as we should. We have the limit as a approaches infinity. We can now perform the integral here, okay? This is a u substitution integral, right? We set u equal to minus st. We take the derivative of that. We're going to get negative s du. And then so we end up needing to divide by negative s in order to make this work, right? So the integral here is e to the minus st over negative s. And we need to evaluate from 0 to a. We have our limit here. We can factor out the negative 1 over s. We have those two expressions here with negative s times a and then negative s times 0. We can take the limit. This is the only thing where the limit matters, right? If we allow a to increase without bound, we get e to a very large negative number, and the limit that goes to 0, right? Because 1 over a large number is a small number. And so what we end up with is negative 1 over s, 0 minus 1, because e to the 0 is 0. Negative signs undo one another, and we're left with 1 over s, which makes sense because s is greater than 0, so we don't have to worry about 0 in the denominator. Make sense? All right. Okay, so this we have just snuck up on Laplace transform of 1. Because this is the integral that we just computed, right? Same thing. Okay. So good to start keeping track of the functions that we know Laplace transforms for, because we're going to end up needing to know a few. All right. There's some other things that we're going to have to make sure that we are aware of. For instance, this may be something that you remember from calculus 2. we have an integral of this form. We want to answer the question, which values of p allow this integral to converge? All right. Now, at some level, this can just be kind of talked through, right? But for the ones that are going to work, we're going to want to make sure that we show things relatively explicitly. Let's suppose that p is less than 1. Okay? If p is less than 1, negative p is greater than 1, right? If negative p is greater than 1, then that means that I'm taking t to some power greater than 1. Doesn't that become a problem? The function's not decreasing, right? The function's increasing. And if I take the integral of an increasing function over an unbounded interval, there's no way that that thing's finite, right? So these values definitely get thrown out. Okay, so at minimum, we're going to need p to be greater than 1, or greater than or equal to 1, right? Okay, if we set p equal to 1, we have this. We just did this problem, this diverges, right? P is greater than 1, we can look at what the result is here, okay? This is going to be equal to the limit as a approaches infinity of the integral from 1 to a t to the negative p power dt. This is something that we can integrate using the power rule because we know that we're not going to get logarithms or some nonsense because we've isolated that case already. Increase the power by 1, divide by the new power. So 1 plus p is this, and we divide by the new power. We evaluate from 1 to a, and we get the limit as a approaches infinity of a to the 1 minus p power minus 1 to the 1 minus p power all over 1 minus p, right? Now, 1 minus p is greater than 0, right? If I subtract 1 from this, I get something that's greater than 0. I have a very large number being raised to a positive power. Hold on. Sorry. I want to make sure we get this right. Yeah, hold on. You're right. What did I do wrong here? Give me a second. Let me. Sorry, I messed up here. That's not quite right. This assumption is not exactly right. How do I? Okay. This all hinges upon what this is doing, right? As a grows without bound, this thing has to go to 0. Okay. That's basically the story here, right? And so in order for that to work, this value here has to be something that is negative, right? I need the large number to go down. That corresponds to this condition here, right? The p is greater than 1. So I didn't say it elegantly the first time. That's the idea. Okay. So that proves that this, with no other restrictions, is the condition that we want. Okay. Because we could have found, for instance, that p has to be like less than 5 or something, right? Greater than 1, but less than 5. Okay, it turns out any p greater than 1 is okay. Now, this idea right here should, of course, remind us of this kind of expression right here from p series, right? Okay. And in fact, the integral that we have just computed here is the proof that this converges, right? The p series proof should have been done in your Calc 2 classes using the integral test, which is essentially what we've done here, right? Okay. So one of the things that I want to just show from the typed up online notes to save a bit of time here is kind of the next step when it comes to talking about computing these integrals that we're interested in. And that is how we handle piecewise functions. Okay. So here on the screen, at the bottom, there is a function that has jump discontinuities in it. Okay. Where we see that there are clear breaks in the function where it is not continuous. And if we wanted to compute the integral over such a function, the way that we compute the integral would be to just compute it over the piecewise continuous segments, right? Splitting things up every time there's a jump. And the value of the function at the jump doesn't matter. Okay, it's just 1 point. And since we think about integrals as being a measure of the area under the curve, 1 point does not affect the area. So if I remove a finite number of points, I have reduced no area because I've removed a finite number of points times 0 width, right? So if we have some problem where we are using or we need to compute the integral of something, and there are jump discontinuities in it, we just break it up into pieces as necessary, and as long as there are finitely many pieces, there isn't anything to worry about. Okay? And the next step in the process for working with Laplace transforms is to compute a few of these Laplace transforms so that we have an idea of what some of these things look like. Okay? For instance, I've already given away the game when it comes to computing the Laplace transform of 1 because I showed that it was equal to an improper integral that we'd already computed. And there are other expressions, of course, that we'd like to compute as well. All right. Now here on screen, we have the definition of the Laplace transform. And in the online notes, so that you know what it looks like, this particular type of script L, I know when I write it by hand, it looks a little bit different, but this is the one that I believe matches with the notation that shows up in the textbook for Laplace transforms. So when you see that, that is an indicator that you should stick the function f of t, whatever it is, into this expression and take the transform. Okay? And what we need to do in order to get things set up is to compute a few other transforms in order to get things going for us. Okay? So one of the easier ones that can be done here in just a couple of lines is computing the Laplace transform of e to the at. And we see here that we just plug the function e to the at into the integral as shown, do a little bit of refactoring, and then end up with a result that's very similar to the result that we got from taking the inverse Laplace transform of 1, taking the Laplace transform of 1, where instead of getting 1 over s, we get 1 over s minus a, right? And this, of course, should be a pretty satisfying result because if I take the Laplace transform of e to the at, it says that as long as as long as s is greater than a, the answer is 1 over s minus a, right? Now, if a is 0, we get 1 because e to the 0 is 1. Okay, so this still works. All right. Now, one of the more important exercises for this related to the idea of having to deal with jump discontinuities in our functions is given here by example 5. Okay, I have a function that's equal to 1 on the interval from 0 to 1. It's equal to k at some specific value of t, 1 in this case, and then it is 0 from then on. Okay? In order to construct the integral, we build the integral by looking at our piecewise function here. It's 1 up to 1, k, and k is some value that in the picture is between 0 and 1, but theoretically it could be any real number. And from 1 to positive infinity, the function is equal to 0. If I want to take the Laplace transform of a function that is so defined, we write out the definition of the Laplace transform. And we can break things up piecewise, right? So from 1 to 0, the function's equal to 1. I replace f of t with 1. From 1 to infinity, the function's equal to 0, so I replace f of t with 0. And at 1, I can't do anything because I can't compute the integral at a point, right? This is 0 based on what we know about calculus. So that's why I skipped that. So I could have written that there, but we're skipping it because it's the integral over 1 point. Now, this, clearly 0. And the rest is given by this. Now, I wrote them in the opposite order because of the minus sign. So that's why it's 1 minus e to the minus s instead of negative e to the minus s, or e to the minus s plus 1 over negative s, which may be what you get the first time you write it down. And of course, we require that s be some positive value. Okay? So this is another example of some function here. And so the idea is if we have a function that jumps, if we have a function that is 1 up until 1 and then goes down to 0 at t equals 1, then its Laplace transform looks like this. All right. Now, it is important, but not something that I want to spend all week on, to understand that there are lots of different functions that we need to make sure that we take the Laplace transforms for. Okay. There are a couple exercises that are done here for your benefit, so that you can look at on the online notes. For the Laplace transform of cosine, and then the Laplace transform of this, which is a linear combination of functions that you should be able to compute the Laplace transform for, because we've done e to the at, right? A in this case would be -3. And it turns out that the Laplace transform is linear because it is based on an integral. It's one of the nice things about integral transforms in general we tend to whenever we can in order to make them linear so that they're easier to work with. So the Laplace transform of a constant times a function is equal to a constant times the Laplace transform of that function. And the Laplace transform of a sum is the sum of Laplace transforms. Those are the two linearity properties, right? So if you have some constants times things and sums of stuff, taking the Laplace transform, you just take it term by term. It's very nice. And the thing that I was tinkering with at the very beginning of class, seeing how we can get access to it, is this link down here at the bottom. Okay. It doesn't show up in the table of contents, and that's something that I need to fix. It got kind of muddled in the website conversion type stuff, but you can find the link here at the bottom of the 6.1 notes page. And if you click that link, you'll be taken to this page, which is a page that has many Laplace transforms computed. Okay. Now, we've only done a couple of these. We've done this one, and this one's covered in the notes page. All right, but there are obviously several more that need to be worked out here. Okay. Now, I don't have a full house in the classroom here, but I'm getting a couple puzzled looks. So there's some notes that I want to clarify. Number one, this list is a resource. It is not a thing that I expect you to memorize, okay, or to completely without aid reproduce on your own. On your own. So for exams that we have that involve problems where I expect you to compute Laplace transforms, the table will be provided. Okay, there's a question. Yes.
Okay, so I'm assuming there's some confidence that trade off with problems, I would assume. The reason I was confused is like number 13 is pretty complicated. I think, and it's like that one, like I can understand how I use for 14, 15, or 1 through 10, and stuff like that. But 13 is just the one that's done.
Okay. All right. So the question was basically, where do these come up? Okay, and there are a couple of these in particular that I want to talk about. I can't promise that you're going to use every single entry on the list, but we're going to end up using more of them than you think. Okay, so these are included on the list because they're all the ones that are basically possible in terms of the scope of the problems for the textbook. All right, so the first half of these are functions whose names you know of, okay, aren't really surprising that they're there. All right, the only thing that shows up in the first half of the page that you may not have recognized is this, okay? Specifically this symbol here. This is a reference to what is called the gamma function, okay? I don't know if your Calculus 2 teachers mentioned this to you or not, but there is a way that you can turn the factorial function into a continuous function. Okay. And so the gamma function is a special mathematical function that is basically what happens if we take the factorial function and make it continuous. And so the way that you would use the gamma function if you're writing down an answer is just write down the gamma function. Don't try to compute it. Just say this answer is in terms of the gamma function. But if you look it up, and it's just named after the Greek letter, if you look up the gamma function, there will be an explanation of what it is that's going on. And there's a simple formula that relates the factorial and gamma function. Okay. Moving further down the list, the one that the student here was asking about was, I think, number 13, right? Okay, so this formula here is connected to the formula on the line above it. Okay, we see here that this u sub c of t thing looks kind of like the thing that we were just talking about, right? Having a function that jumps down to 0. This function starts out at 0 and jumps up to 1, but it's more or less the same thing. Okay? We'll talk more specifically about this later, but this is an example of something called a Heaviside function or a step function. Your book uses this notation. I said Heaviside. It's named Heaviside after a person. I believe it was an English mathematician. Okay, but it's a step function. And instead of being like this, the Heaviside function is 0 until some value c, and then it jumps up to 1. Okay. If we look at this function here, okay, this is a product of a step function and some general function f that has been shifted to the right by c. That's the way to interpret this. This is a shift by c to the right, okay, which we should know from our transformation rules and our understanding of algebra. It turns out that physically, this represents a way to write down a function that in some sense is turned on at time c. Okay? The u sub c function is 0 up until c and then is equal to 1. Right? F of t minus c is a function f of t that has been shifted to the right c. So if we imagine, for instance, that this looks like this, this would be an example of sine that is 0 until c and then turns on. Okay? And it gives us a way to encode different types of things. This is part of why this material is so applicable to electrical engineering, is because I can imagine some input function being turned on at some point in the future, or potentially turned off if I add some minus signs in the right places. Okay, so that's the utility of that expression. For the rest of these, some of these are just algebraic forms that come up in the process of needing to be able to write down our answers, okay, or make the conversion. This is a special type of operation known as the convolution. Occasionally, it's the easiest way to write down our answers. Okay, this is a special class of integral that comes up in applications. This is a special function that we will discuss later on. And this thing right here is related to how we encode our initial conditions for these problems. So that's later on. Okay? So all the stuff on the table has a purpose, and we'll use basically all of it. But the main point that I wanted to make is that, at least for now, the way that you will need to access the table is this link at the bottom of 6.1, and I will try to make sure that I can get a link, a direct link to the table of contents in the on the table of contents page for the course. All right. So how's everybody doing? You all here? Those of you out in the world on the internet? All right. There's something else that I want to mention before we run out of time, and then what we'll do next class is focus on solving problems. Okay. All right. Okay. All right. Now, one of the things that is somewhat unique to Laplace transforms is that we don't really bother to use Laplace transforms unless we have an initial value problem to solve. It is not worth the trouble at all to go to this unless we are working with something that is cast as an initial value problem. And the utility for this we will see as we work one of these things out. Okay? So let's do an example. All right. So we have y double prime plus 2y prime plus 4y equals 0. Our initial conditions are 0 and 1. And what we want to do is we want to apply the Laplace transform to both sides of our equation. Okay. Now, Laplace transform of 0 is 0 because it's the integral of 0. But where things get interesting is how do we deal with stuff like the Laplace transform of y double prime. Okay. And we need to make sure that we understand what in the world is going on with that. Okay. So let's start with just y prime. Or f of, or f prime, however you want to think about it. But by definition, we have the integral from 0 to infinity of y prime of t e to the minus st dt. Right? Just plugging in y prime for the function that we want to take the Laplace transform of. If we perform the computation here, this is something that we can compute by integration by parts, right? So we do that. And what we do is we set dv equal to y prime because that's the thing we want to integrate, and u is equal to this, right? And so what that's going to give us is the absolute value of y of t e to the minus st evaluated at 0 and infinity plus the integral from 0 to infinity of y of t s e to the minus st dt, because we have to integrate e to the minus st to go from dv to v, and the integral of this is this. Okay. We evaluate this here, right? Evaluating this requires a limit. We're going to have the limit as t approaches infinity of y of t e to the minus st. That's just this part, right? That goes to 0 because e to the minus st is t and goes to infinity, goes to 0. Right? Because we're assuming that y of t is some reasonable function. Right. So this time has to go to 0. This is 1, so we're just left with minus y of 0, right? And then this thing is just s times this. Which we can rewrite because this part right here is just a Laplace transform of the original function y. Okay? Now, it turns out that this kind of gives us a pattern that continues for any number of derivatives we need to take. So if I'm talking about the Laplace transform of y double prime, I'm going to end up with this. Just due to repeated applications of integration by parts and computing things like we did here. Okay. The work is done a little bit more carefully in section 6.2 of the notes, showing the process of how these computations go about. But basically the pattern follows. Okay. And so for us, what it allows us to do is, number one, employ the linearity property of the Laplace transform and take the Laplace transform of each of those terms individually. And so what we can do, and I'll write it piece by piece this one time so that it's clear what we're doing. And then we have s squared, okay? And what I'm going to do is, instead of writing the Laplace transform of y, I'm going to write capital Y of s. Okay, again, calling back that relationship that I mentioned before, where lowercase and capital letters are the function in either the t domain or the s domain. Oops, sorry, forgot the rest. Minus s times y of 0 minus y prime of 0 plus 2 times s times capital Y of s minus y of 0 plus 4 capital Y of s equals 0. All right. All makes sense? Yeah, y of s is just a different way of writing this. Less complicated notation. So it is the representation of the solution y in the s domain, whereas lowercase y of t is the solution in the t domain. Our goal ultimately will be to isolate this function and then be able to convert it back into the t domain, and that'll be our answer. Okay, so now what we want to do is, you'll notice that taking the Laplace transform of our function y requires that we have initial values to plug in for the derivatives, right? If I don't know what those initial values are, taking the Laplace transform does me no good. Okay, so this is why we say that initial value problems are basically required in order for these things to make sense. Okay? Now, y of 0 is 0, and y prime of 0 is 1. So we want to plug those values in. Okay? And so we're going to have s squared, and I'm going to go ahead and combine like terms here. All of this stuff times y of s. And the only other surviving term I have is this negative 1. Okay? And so what this allows me to do is it allows me to rewrite this expression isolating capital Y of s and the final step in this process is to manipulate algebraically the expression that I just wrote down so that I can use the right-hand column of this table to figure out what function of t corresponds to my capital Y of s. All right? Now, it turns out that the expression that I have has a quadratic in the denominator, right? So it may or may not be easily factorable, but I'm looking at these expressions here that involve sine or cosine somehow. And so what you do is you manipulate the denominator into some form that is helpful. And once you do that, you can use the table to perform the conversion. Okay, so the starting point for us is probably going to be to do something like completing the square in the denominator. Okay, so we look at our expression here. And we can rewrite this like this, right? Which conveniently for us makes everything look like a perfect square in the denominator. Okay. And the form that it turns out that we're going to try to match here is going to be this form from the table. Okay. And then I may need some constant k out front in order to get everything to line up the way that it's supposed to. Right? We can see by comparison that a is -1 and b is the square root of 3. Right? And I need b in the numerator. So what you do is you multiply by 1. It looks like this. Right? And according to the table, what this tells us is that y must be 1 over the square root of 3 times e to the minus at sine of bt, which is equal to 1 over the square root of 3. Sorry, there's no minus sign here. A is -1. I messed my minus sign up here. I apologize. A is -1, and b is the square root of 3. Okay, because that's s minus -1. That's how I get s plus 1. All right. So there is an art to this, okay? And the art comes along with progressing to the point in the problem where you have capital Y of s equals a bunch of stuff that just has s's in it. So you get Y of s by itself on one side of the equation. Here it's capital F of s, but it's the same thing, right? And then you start looking at these and ask yourself, which one of these or which combination of these, because sometimes you need more than one, can I algebraic manipulate what I have to match? And so that is the process. So the art to this is doing enough practice to where you have a feeling for what direction to go. Can you look at what you have and figure out how to manipulate it to get what you need? All right. We'll be practicing that. We'll try to do as many problems as we can next class to get everyone some experience built up while also introducing some of these other functions here whose transforms show up later on in the list. All right. I apologize for stealing a few minutes here. Take care, everybody, and I wish you a good evening.